I'm Michael Herrera. This is the Physics 1B extra credit Archimedes Principle Lab. And, okay. So this is the initial diagram. This is the final diagram. I'm going to get ice for the first trial, just pure ice. Put it in water. We know that the density of water is greater than the density of ice. This is the free body diagram here. There are two forces acting on the ice. Gravity, which is mass times little g, and the buoyant force, which is the density of water multiplied by gravity multiplied by the volume displaced. So it's going to float initially because the density is the density is less than that of water. So using Newton's second law equation, we know that there's no acceleration. So the buoyant force must be equal to gravity, or to the gravitational force. And the Archimedes principle says that buoyant force is the weight of the water displaced. Or in the equation here, like I said earlier, buoyant force is rho water, volume displaced, times gravity. So this entire area down here is the volume displaced. So if you put mg equals that equation I just said, you can cross out gravity. And also we know that the mass of the ice is the volume of the ice times the density of the ice. So if you plug that into the equation, you get volume of ice, density of ice, equals volume displaced by density of water. You can move that around a little again and get density of ice over density of water equals volume displaced over volume total of ice. And this will give you how much of the ice is floating above the water. So if you take it back a little bit, so we have the volume of the ice multiplied by the density of the ice is going to equal the volume displaced by the density of water. Density of water and density of ice are constants, but the volume of both sides of this equation is going to decrease. So it's kind of hard to explain, but in this picture right here, this is the initial mass, or the initial volume of the ice on the outside. This is along after a certain time. You know that the mass times the gravity of this entire area is going to convert to just pure water. And the volume displaced of the entire thing is going to equate to pretty much just the standard volume of water. So in my prediction, it will remain constant because we know that the density of water and the density of ice melted is the same quantity. So when it has a greater density, when it has less of a density, it's going to float above. Once it all melts, it's going to be exactly constant, is my prediction. Okay, so here's my solid block of ice. I'm going to put it in here. Oh, shit. Yeah, so it's in there. Let me fill it up with some extra water. So, an important part of this lab is that sorry, that cup's not working. An important part of this lab is that the container is completely filled with water. That way we know whether or not any of the, okay, you can see here it's filled totally to the brim, and you can see that there's a little bit of ice above. So what a lot of people think is that this mass, this volume that's above the surface of the water, once it melts, it's going to go into the container and overflow over. But because of Archimedes' principle, we know that that should not happen. So to get the volume of the ice, with just the pure ice, with the nail in the ice, and with the bubbles in the ice, for all of those situations, I use the same cup. That's this normal styrofoam cup. And I wrote the dimensions here, charted it on an XY axis. figured out the slope and did a little calculus here to figure out the volume. Spun it about the x-axis. So came out with 292.9 cubic centimeters, converted it, it's 2.829 times 10 to the negative 4 meters, cubic meters, I should put a 3 there, of water displaced. So Archimedes principle, the equation is the buoyant force is equal density of water, volume displaced, gravity. So density of water is 1,000 kilograms per cubic meter. Volume is what I figured out here. And G, we're just taking to be 9.8 meters per second squared. So that's 2.774 newtons of force upward. Now, with the ice that we see melting here, the density of solid water is less than liquid water. So you can see there's a little bit of volume on the top, but the buoyant force, that 2.7 newtons, is going to be greater than mass times gravity, which is pulling it down. With the nail, which I'll show you after this, we're going to have a nail in the ice here. Hopefully that mass is going to overcome, well, we had something happen. Hopefully that increase in mass is going to overcome the buoyant force. So the volume will be exactly the same because it's occupying the same amount of space. But if m times g is greater than 2.774, then it'll sink. Same thing when there's bubbles in the ice. It's going to be a similar situation to this, but it should float even higher because you're going to have air in there, which is much less dense than either solid or liquid water. So I'll give it a few more minutes and see what happens. But as of right now, there's no water overflowing. We know. So I'm just using like a spring-loaded weight here that's kind of used for weighing stuff around the kitchen. So it's not going to be completely accurate, but since we figured out the buoyant force is 2.774 newtons upward, and we know that this is stationary, not going down, the force of gravity should be less than that 2.774. So let's figure this out. Put this on the scale. This is another cup I had. It's just pure ice. It's reading, it's about 232 grams, so 0.232. Let me get my calculator. So that's 0.232 kilograms, and you multiply that by gravity, which we're just taking to be 9.8. That's 2.2736 newtons. And the buoyant force is 2.774 newtons, so that makes sense. The downward force, which is this, is not as great as the upward force, which is why we're seeing a little bit of ice above. Alright. Okay, so the ice is pretty much completely melted. You can see here there's a little bit left, but the water level is constant. It may have decreased very slightly, but that's because there were a little bit of bubbles in the ice. But for the most part, the water is level. Okay, now we have the ice with one screw inside of it. Now, the volume that it occupies is going to be the same that we calculated earlier. And because of that, the buoyant force should be 2.774 newtons upward. But let's weigh this on the scale here. If you want to zoom in, it is a little over 300 grams. Yeah, 300 grams, so 0.3 kilograms. So if we get the calculator here, we know the gravitational force is going to be 0.3 kilograms times 9.8 meters per second squared, 2.94 newtons. So 2.94 newtons is greater than 2.774 newtons, so it should sink. So here we go. Gonna get the ice out of styrofoam cup, and once it sinks, now the volume of ice that would have been floating above, the volume of ice that would have been floating above is going to be forced downward. And once it melts, that less dense ice is going to convert into denser water, and some of the volume should decrease. So let's see if this thing comes out. Okay, there we go. It's got a hole in it, but whatever. Alright, and then we're going to fill this all the way to the brim. And notice that it did sink. And if you could zoom in, Michelle, see that the brim it's totally to the brim with water. So if the volume of water increases, it should spill over. But you can see that the screw is down here. The gravitational force overcame the buoyant force in this case. So we'll give it a little while, see if it melts, or see when it melts if the volume decreases like I predict. Okay, so most of the ice has melted at this point. You can see the screw is at the bottom. There's very little ice, and it's hard to tell on camera, but the volume has decreased very slightly. And the volume decrease should be equal to the initial volume of ice that was, not in this trial, but in the previous trial, the initial volume of ice that was on the top. It decreases by that same amount, which wasn't very much. But alright, on to the next trial. Okay, so I had trouble finding ice with bubbles in it. So instead of that, I just did ice with a lot of screws. The only difference here should be that the gravitational force, because the mass is increased so much, would be much greater than the buoyant force. So the only difference is going to be, in effect, all of the metal in here remains ice as far as the buoyant force is concerned, because that volume is constant and it never turns into a liquid and never turns into water. So the volume that decreases should be less than what we saw with one screw. But the volume should still decrease. So it's going to be pretty much the same thing, I'm thinking, but not as dramatic. I maybe should have done this one before I did the single screw experiment, but here we go. So I'm just loosening up the ice. Oh, shoot. Forgot almost. So the mass...
Should we restart?
No, it's fine. The mass is pretty much at the limit of this scale. It's pushing 500 grams. So let's say it's 490 grams. So here we got 0.49 kilograms multiplied by gravitational force 9.8 meters per second squared. That's 4.802 newtons, which is much greater than 2.774 newtons of buoyant force, because as you see here, it's the same container, the same volume of water. So now gotta melt it a little. So when this is in the water, obviously all the ice is going to melt into water, but the metal stays metal. Its boiling point is much higher than what we can get here. So the volume will decrease, but the volume that the metal occupies is going to still displace that water. Alright, hang on. There we go. Okay. Alright, filling it to the top again. You can see that it's not even close to floating. It's almost twice the amount of the buoyant force. So we got it filled up to the brim again, and we'll give it some time, and hopefully the volume will decrease as I predict, but not as much as it decreased the last time, so it might not even be noticeable. But here we go. Okay, so just as a little added bonus here in this physics lab, I took the pretty much freezing water, put it into the boiling pot, and the glass cracked. So we haven't talked about that, but I'm sure eventually we'll find out why that happened. Yeah, but there you go. You can see right now, not all the ice melted. I was trying to hurry it up, but the volume decreased not as much as last time, so the prediction should be accurate, I think. Yeah, alright. But because of Archimedes' principle,